first speaker that we have right now is Brent from the Aerospace Corp. He's currently works for the Aerospace Corporation within the cybersecurity subdivision as a senior cybersecurity project manager, and as a former civil servant at NASA, where he led various cybersecurity efforts and was awarded NASA's Exceptional Service Medal for his landmark cybersecurity work in 2019. I guess that's pretty impressive. Bailey has extensive experience in tests and evaluation of systems and technology using high-fidelity digital twins with a specialization in cybersecurity. In his work at NASA, he built and managed software testing and research laboratory to include a robust cybersecurity range containing many digital twins and spacecraft technology. And coming from the academic side myself, I can definitely say that Brandon is well known in the community and makes really excellent work. So the stage is all yours.
Thank you. Yeah, so basically a little on the background just to provide some, I think this block here from this 5-6 year span of having the luxury of being able to pen test and attack mission critical infrastructure systems, you know, from deep space rovers to ground infrastructure for International Space Station and things like that. So I've had a lucky career from that perspective, and we'll kind of jump into basically being able to use all that knowledge of all the tests on operational systems, as well as research using digital twins and real hardware to drive what we're talking about today. So what we're going to talk about today is really the space attack research and tactic analysis framework that we've built, Sparta, which is a spin-off from like the MITRE ATT&CK framework, and you've seen some other agencies works in this area, but this is kind of our version of what we're doing. So let's kind of talk about the cybersecurity problem in space, at least from the kind of the U.S.-centric perspective. Is what we have is we have a high dependence on encryption and authentication. Not everyone does it appropriately. Some do it well, and then there's maybe some transect mixed in there with occasional tempest controls for like electromagnetic emanations. So, but that's kind of in the military space. So if you look at commercial and civil space, it's not, you know, they're varying from that level. So most people are doing encryption authentication, but it's not holistically, especially in some of these smaller satellite communities. You'll find them unprotected. So what we found was through our research and using kind of our attack model here, which is just a picture, you probably can't see that well, but we've built like a threat model that's on our Sparta website that talks about, you know, tiered adversary, script kiddie, tier 1 through tier 7, which is, you know, nation state APT level stuff. And then we've built kind of TTPs and threat analysis based on that threat model. And if you think about how you can attack a spacecraft, a rogue ground station or a rogue spacecraft is one mechanism, but there's also many more attack vectors. And that's what we wanted to really enumerate with the work that we were doing, is because what we found in the initial research when I started looking into this a few years ago was we saw a lot of publications out there that say, hey, cyber's a problem for space systems, but they don't tell you like what part of it. It's a black box. It's the boogeyman that'll get you if you don't pay attention to it, but no one tells you what exactly the problem is other than the word cyber. So what we're trying to do is decompose that down and really get to the nitty gritty. And we're trying to really publish as much information in the public sector, which sometimes people don't like because you know, they feel like, well, why are you putting all this information in the public sector? And I think, at least on the U.S. side, we see a trajectory of utilizing commercial satellite, commercial technology, and we feel like if you just keep this under lock and key from a government perspective, then it's, you know, you're going to do yourself a detriment because you're not going to be able to depend on those commercial services over time. So we want to get this data out there. So what have we done thus far? And by the way, these charts, I know that's a common question. These charts are already on the internet. I'll show you a link at the end so you can just pull them down and go from there. But basically what we did was we started a couple years ago and wrote a really detailed report on cyber protections for a spacecraft. And after going through that process and that evolution, we realized, okay, writing a static PDF document is great, but how are we going to maintain relevancy and keep it up to date? And that's where Sparta comes in, and that's what we're going to talk about. So if you've read that spacecraft, what we call a TOR, Technical Operating Report, if you haven't, I would suggest you read it. It gives you some good background on why we need to be doing this in the first place from a spacecraft perspective. But we've basically evolved that work into what it is today, which is Sparta. So, and what we're trying to do is basically utilize threat-informed TTPs to drive cybersecurity requirements. So we're not necessarily in the compliance game. We don't want to just drive compliance exercises. We want to actually put requirements in on the books. So what we've had some success in thus far is utilizing Sparta and utilizing TTPs and threats to drive shall statement requirements to be put in acquisition documents, as opposed to saying thou shall comply with standard 1, 2, 3, 4. It's here are 250 shall statement requirements on how you need to build the security principles on your space vehicle. So that's where we're trying to push the market of establishing that granular security procedures up front using threats and TTPs. So this is just a summary of a chart. We've seen several of these. The takeaway here is cyber attacks continue to increase. It's somewhat proportional, at least based on this research, which was Cybersecurity in New Space, it's somewhat proportional to the number of satellites that are getting deployed. So if you look, there's an upwards trend of as we deploy more satellites, more security incidents are recorded and that type of thing. So we don't need to dive into all these details, but this is kind of the takeaway is the threat environment's changed. There's more attacks happening, and we need to make changes. So how are people attacking systems? That's the one thing. So like that's the key that you need to understand. So from the White House put out Space Policy Directive 5 a couple years ago, and they defined the necessity for commercial and the U.S. government in general to secure space systems. And when they define space systems to include the ground network, the sensors, and the vehicle alike. So it's important to understand when you say secure a space system, it's like that means the spacecraft too. It doesn't mean, well, let's just do the ground security and we'll be good. It's all layers, right? It's the sensors, it's the payload, it's the firmware, it's the satellite itself, it's the supply chain, it's all those things. So I think I heard an individual mention to me today in one of the coffee breaks about some maybe European standardization or legislation coming out that excludes the spacecraft from kind of the security procedures or security requirements. I'm not sure. It's an interesting take. From my perspective, I think you're only as strong as your weakest link, and if you don't have proper implementation of security on board the vehicle, you're going to have some issues. So I hope that's not the case. So what we tried to do was say, all right, how do attackers actually attack a system? So threat actors will initiate some sort of threat action or TTP to exploit some sort of vulnerability to have an impact. So what we did in our research was says, well, how are they actually doing it? What would it look like if someone was actually going to do this, and how do we implement countermeasures to stop it? And that's really where the Sparta stuff came into play. So we tried to fill the gap of TTPs for space. So if you were in the room a couple of talks ago, you saw ESA's implementation of something similar that they call Space Shield. And interesting enough, we were working in parallel, and we took a lot of their work that they did and implemented it in Sparta as well. And now that their data is public, we'll even do a more cross-reference to that. So we're going to try to maintain a superset of all TTPs that can impact the spacecraft, including ESA or the Canadian fellow that was here earlier. So we're going to try to be the superset of all these things. And if you want to have your own version for a smaller set, that's fine. But we're going to try to make sure we have a superset, because what we're really trying to do is fill that knowledge base of how adversaries can attack a spacecraft and a space system in general. So what we're trying to do is leverage what we considered the industry standard, which was the MITRE ATT&CK framework process, which is tactics, techniques, and procedures. And we're mimicking that, so I'm not going to belabor that issue. So at the time when we launched this in October of 22, it was really the first body of knowledge that was ever put together like this that really break down how you actually would attack a spacecraft, in addition to all the countermeasures and things that go with it. So it's important to understand that the TTPs are really just a mechanism to drive your defensive action. So we're not trying to document TTPs for the sake of, oh, it would be cool if we just documented all the ways you could attack a spacecraft. The point of the whole exercise is to utilize that information to drive the security controls and security principles that you're implementing on the vehicle. And that's what we're trying to do. And what's interesting to a lot of people is this is all unclassified on the internet work. And it's going to continue to be that way. And how do we get here? It was basically 3+ years of work, of papers and research and talks at DEF CON and all sorts of things like that. So there's some links in the backup that show all these papers and things, but it wasn't just, hey, let's go do this for a 6 months exercise. It was multiple years of research into kind of figuring out how spacecrafts can be vulnerable. And so we're trying to really ensure that we have we improve space resiliency by educating people on the TTPs that are out there in this publicly releasable tool. So let's get into the actual interesting things. So I just wanted to set the stage on like what Sparta is. So let's talk about how you could actually use it to build attack chains, and then understand what kind of countermeasures you can derive from those attack chains, and all the data that's kind of in this wealth of knowledge. So we're going to go through 2 attack chains that I've presented prior at DEF CON, and then we're going to do a couple of new ones I did just for this talk. And then in the backup, there's a theoretical one on the PC spoof vulnerability for time trigger Ethernet that people could review if they want. So let's kind of go from a blast from the past. So this is a very basic attack that was it's on YouTube, that shows you how you do a basic replay attack on a space vehicle. It goes through and breaks down the CCSDS protocol and does all the details of how that works. But what does that mean in the context of Sparta? So basically, the attack was you record your telecommand link going up, and then you replay that telecommand link to the vehicle. And if you don't have proper encryption, obviously that will fail. So, but the attack in DEF CON was really geared around, one of the attacks in that presentation was forcing your spacecraft into a clear mode, then launching the attack. So it wasn't that the system didn't have encryption necessarily. It was you've maybe jammed the GPS, or you've done some sort of fault injection technique that puts it in a clear mode. Then you can launch a replay attack. That was kind of the premise of that talk. But how does that work in the context of Sparta? So what you do is you use our navigator feature in Sparta, and you can go through and you can click individually each TTP that you're using for your attack chain. And then you can export that data out to use it for countermeasure analysis and things like that. So what does that attack look like in practice? So I wanted to kind of step through individually using screenshots to kind of articulate what would happen. So the first step of a replay attack in this simulated incident is basically you need to eavesdrop right on the RF link as it goes up. So in our simulation, we were basically listening as the ground terminal was sending no-ops to the vehicle. So you see those come up, and we've recorded that traffic, and you see, like in this case, the command counters increase, and it does what it's supposed to do. So if you replay that, obviously your command counters go up, and you see those commands process. So that's not a very exciting attack necessarily, but it's kind of just introducing you how you use this. So another thing you could do is with that same type of attack is you could implement some sort of mechanism where you change the bits of the CCSDS frame to do something different. So this is obviously the danger of not doing encryption in this case, which is pretty standard these days that people do encryption. But if they don't, you can just record basic no-ops potentially, and then you can, from an eavesdropping or reconnaissance perspective, then you can change the bits of the actual packet stream in the signal and then retransmit it, and then it has a different effect. So in this case, the bits that I changed made the flight software reset one of the applications in that one. And so what you see is how these attack chains kind of work, right? So you got some reconnaissance from an eavesdropping perspective, you got some execution from a replay perspective, and that type of thing. So that's how you walk across the attack chain. So that's kind of what that looks like. So then what you would do in Sparta from that perspective is each individual TTP that you have has a corresponding countermeasure to it. So you can basically click on any TTP that's in there, and it'll say, okay, well, how do you mitigate replay attacks? Well, you have ComSec, or you have authentication, or you have replay protection built in with like COP1 or some other sequencing mechanism that you have. So that's kind of the premise. So just kind of setting the stage for that. So another attack chain, which was from DEF CON 22, which is memory injection. So in this attack, basically what we were doing was in a PowerPC with VxWorks, we use fuzzing to figure out sensitive memory locations that will cause fault conditions in VxWorks on top of the PowerPC architecture. So we did a lot of fuzzing and things, which the subsequent slides we'll talk about, to find that sensitive memory location, and then do the attack. So if you look at the attack chain, the way it looks, right, you have to understand, okay, there's some fault management. I kind of need to understand a reconnaissance of what their fault management strategy is for certain injects. I need to maybe, if I'm coming in from the ground system, I got to compromise the ground system. I got to disable the encryption. Then I run my exploit, which is like writing data to the memory location, and then I'm having some sort of impact on the end. So this is kind of how that works. So this research was basically showing, how we got to the point where we knew where to poke the memory, which was as a recon step, right? You go through and you read. One of the interesting things about the space sector and embedded systems in general is the manuals and the design artifacts are extremely beneficial. So like they tell you how to create faults or how to manage faults or inject faults into the system, or what will cause a fault and what will cause an exception. So that from an attacker standpoint, then you just need to leverage that. So, you know, while buffer overflows and traditional cyber vulnerabilities do happen in the spacecraft firmware, like we saw from your presentation with the firmware, many times from an attacker standpoint, you're just really just leveraging the system against itself in the space world, because it's a cyber physical system, and there's so much trust built in between the ground infrastructure and the space vehicle that you can basically turn itself against itself. So like from an insider threat perspective or compromised ground perspective, it's a lot easier to do this. So we just reviewed the documentation and figured out where to inject into the memory for that to happen, and we used a digital twin to do that. And that talk is in much more detail from DEF CON last year. It's on YouTube. The link's there. You can dive into that if you want. But the point of this was basically just to show and articulate kind of how this attack chain would look from a Sparta perspective. This one would be injected from a compromised ground system that already has the encryption keys, and you're able to just send the packet that the kill packet that basically goes up to the flight software, and the flight software will, in this case, this flight software has the ability to take information directly from the ground and write data to a specific memory address, because that's where you get into least privilege not being enacted, and the flight software has access to the entire memory space, and then you can basically just crash the system. So that's extremely common in space vehicles. Everything runs as root basically, or in the real-time operating systems like VxWorks, there's not proper threading and segmentation from a privilege management perspective. So if you can get into the data stream or get into the ground, it's pretty easy to do. So that's kind of what that attack chain would look like. And then what you do there, right, each one of those, you'll have countermeasures that kind of go with what would be there in that perspective. And something you can't see that well probably from the audience, which I think I'll show in some other ones. Right here on all the countermeasures, so America is basically standardized on NIST risk management framework, 853 revision 5. So every countermeasure that we have in our database has correlative NIST controls. So we're not an ISO 27000 organization or country necessarily. So we're all in the RMF 853 series. So we make sure that we have a cross corollary to that. So like if you say, process whitelisting, right, as a mechanism, right, that's a CM7 and SI10 family control. So we want to make, because a lot of our legislation's written from a FISMA perspective that says you have to implement these things. So we make sure that we have those linkages, because then we have the policy to back up what we're saying, basically. So you'll see that. So another attack, this was another one that we built. This was custom for this one. So this was, again, reviewing documentation of like the flight software design, which in this case was an open source flight software application, the CFS application from NASA. So basically we were reviewing that and realized, okay, they have these things called relative time sequences to execute at boot. So if you can inject malicious data into the supply chain from that perspective, then you can have code executions on the vehicle. So you can do that at the binary or the source code level. So in this case, just as a proof of concept, just to simulate a compromised supply chain, because what we're trying to do is educate on these attack vectors so that then people can see, all right, would we have found this, right? So in this case, what we would be testing is we injected a couple of commands in this relative time sequence in the development environment, and you would say, would your analysis tools find that type of thing? Because it's not really it's not like you injected a buffer overflow, right? You commanded the vehicle to do something that it wasn't meant to do. So, this is like a simulated software supply chain attack, and it injects code after 60 seconds after boot to do something different. So that is in the Sparta framework, right? Compromised supply chain, malicious code injection, time synchronized execution, and then disrupt and denial from an impact perspective. So I hope you're kind of understanding the point to a lot of this is these are all examples. So when you think about why TTP matrices are important, how you implement a relative time sequence time bomb inject into the supply chain for a CFS application, which is NASA-based, is going to be completely different than you do maybe for an ESA mission, because it's going to be different. But the TTP is the same, right? How would you actually execute a relative time sequence time bomb in this architecture? And you kind of walk through that and see if you got the countermeasures to do it. The last thing here is basically, the next thing is just a reaction wheel attack, which is pretty basic. In this case, this CubeSat has a reaction wheel. And you're able to utilize, in this example scenario, it's a CubeSat that doesn't have encryption or authentication, which is, some CubeSats don't. So this whole thing was showing, how you could do an attack and create a CCSDS frame to basically transmit data. So this is the CCSDS packet that you would send, in this case, to this flight software that would cause some sort of reaction on the vehicle. And what we did with this attack was basically, do reconnaissance, understand how the commands work, compromise, do command link intrusion from a rogue ground station due to no authentication, and modify the onboard attitude, determination, and control with the attack. So what that looks like is, that's not what I want to do. So what you'll see is after a minute, we transmit the packet, and then the spacecraft tumbles. Now that's sped up for demonstration purposes because it was slow to see, but yeah, that's the type of thing. And then so from an attack perspective and a defend perspective, like you build these attack chains and you say, all right, these are the 3 or 4 attack chains that I feel like have a high likelihood in my system. Like then how do I build build protections against that? So what that the kind of the punchline here is this. So in this example, those 4 attack chains that I just developed, that's kind of like our risk assessment of like these are the most likely if this was a made up fictitious space system. And we said, all right, let's these are the most likely attack chains based on our analysis. You throw those in Sparta and you light up all the TTPs, and what that does is then you can export out in Excel all the countermeasures that and controls that are necessary for you to kind of be resilient against that. So these TTPs that are listed there translate to these level of countermeasures, and then if you're in the RMF world, translate to these controls. So this is a way to do like threat-based analysis to get to like controls is the thing. And lastly, what we have in there is the ability to go into the GUI in Sparta from a countermeasure perspective, which is good for some people. Is they want to know, all right, well, if I implement this control, what happens? So you can go into Sparta and click on individual cyber protections, countermeasures, and then you'll see in the GUI things turn red and green based on what you're picking. So like in this example, I said I want to build a mission that has ComSec and TransSec only. So then you see, all right, well, that's going to protect against the green ones to some extent, and the red ones it doesn't cover. So it enables you to start seeing, all right, where your vulnerabilities could be from an attack chain perspective and a TTP perspective, doing that. So with that said, I think this is probably one you want to snap a picture of. But like I said, it's all online on Sparta. There's a website. It's all on the sparta.aerospace.org, the whole presentation, so you'll be able to just grab it from there. But these are a bunch of links that you can have, some media coverage, some other things, that type of thing. So, and there's another slide that has all sorts of aerospace resources. These are just hot links, so you can't really do much with those. With that said, I think we could probably take a question because I think it's been about 25 minutes.
All right, thank you very much. So we have a first question online. All right, Brendan, if zero trust would have been implemented, for example, every single digital identity secured by a X509 certificate plus every single software signed, would these attacks been possible?
Yeah, so the X509, from a software perspective, I guess if you signed every command, but so some of these things, if you use the authenticated ground system, not a rogue ground system, it works, right? So if you inject into the supply chain, like the RTS example, that would work because that was that's like SolarWinds, right? That injected prior to the software signature happening. So the malicious software is signed in that example. So yeah, the one that probably wouldn't have. No, I think all those would have worked because that would have been. It depends on how your DevOps process works, but you would have signed the malicious software package before it went up.
All right. Do we have some question from the room? Okay, then I have a question. So when you started building the Sparta matrix, you mentioned that you went through a lot of research. What was your original intention how Sparta would be used? Was it like intended for academia? Was it intended for government organizations? What was your like original goal?
Yeah. So the kind of the stated goal and original goal is system engineers. That's like my number one priority goal for Sparta, is so that system security engineers can utilize Sparta to figure out where they have gaps and where they need to implement countermeasures. There are a few other different use cases that we promote. One's like from a defensive cyber operations perspective, so like at the SOC or the ESOC level, on monitoring your ground infrastructure. So if you're monitoring your TT and C-Link telemetry and the commands, you would be able to build correlatives from a DCO perspective on the ground. And then third one is another one that's really good, and the space ISAC is going to be huge in this one, is the threat intelligence. So if you've ever done research in space and cybersecurity, there's like no way to trend and understand over time what are the most prevalent TTPs that are out there that are attacking space systems. So now that we have our own kind of framework, and if we all standardize on something like that, we can track and trend over time the TTPs from a threat perspective. So those are the three main use cases, but the number one is the system security engineer is what we're going for, is to educate them on the countermeasures.
All right, very cool and impressive. We have a few more questions online. So, is there also an assumption of no authentication of the commands sender in attacks that are going on to modify the commands?
Well, it depends on where you inject the attack. So like, and these are just obviously made up scenarios. So like I said, if you inject the malicious command at certain points in the infrastructure, there's no protection against it necessarily. The spacecraft will have to protect itself. So that's why it's important to understand like building like onboard intrusion detection type capabilities, so that it can maybe detect that there's malicious commanding that's happening. Like, hey, wait, I'm not supposed to do that, or I've never seen this command sequence before. So it depends on where you inject the modification. Several of these attacks have been launched with encryption and authentication activated, and we've done numerous experiments and tests from that perspective. But that's usually from a compromised ground perspective or a software supply chain perspective.
All right, we have one more question. You mentioned that not many CubeSats use a link protection, any link protection. Do you have any quick wins to minimize risks to satellite, whether small or large?
Well, I would say using quick win would be just use SDLS from a CCSDS perspective. It's software-based encryption. It's got good algorithms. It's got authentication and encryption built into it. So I would say that's a quick win from the perspective of if you're building the system. If you already have a CubeSat up there and you don't have any authentication or encryption, then I would say there's certain telemetry values that you can monitor. We have a paper that talks about some of those, but just command counters and things like that are probably your best option. But SDLS on the command link, data link layer encryption, which is software-based crypto, should be sufficient for a CubeSat and doesn't really have any effect on swap other than a little processing power.
All right. Thank you very much again. Oh, we have one question. Let's see.
Hi, Wong. Do you consider also the user segment as well as the ground segment interrelating to or also regenerative payloads?
So Sparta's really focused on the space vehicle side. So on the payload side, there's several TTPs that are listed in there that are related to payloads. So like basically payload hopping from payload to main bus, and talks about that as an attack vector for lateral movement. And then there's mitigations and countermeasures from that perspective. The user segment, not really, because that's just like a ground attack basically, or maybe modifying the data from an integrity perspective. But Sparta's really meant for the space vehicle side, because from a TTP perspective, we feel like MITRE already kind of has a lot of the ground and user segment covered, and we don't want to repeat work. So it's basically from a TTP perspective there. But now I would say the countermeasures that we have listed in our countermeasure database, a lot of them transcend space ground or user. So like, you know, especially like software supply chain, like software bill of materials, coding standards, vulnerability scanning. There's a lot of things in there that are already listed that just can go anywhere because it's just standard security practices. But some of the stuff that's more niche to the space vehicle obviously doesn't apply.
So to consider the whole different segments, it should be not only using Sparta, but also MITRE ATT&CK for the ground segment.
Correct. Yeah. So there's a whole different conversation and presentation on that perspective. And there's actually a paper written by MITRE called Pivot, Platform Independent Vectors of Technique, which talk about the need for understanding multiple attack matrices to understand your full attack lifecycle. Because like if you think about it, like in the industrial control system world, and you look at some of the case studies like Black Energy and some of these other destroyer, so they use enterprise TTPs to a point, then they pivot to ICS, and then they use ICS TTPs. The same thing's going to happen to space if you're using ground infrastructure to launch your attack. If you're using your ground infrastructure to launch the attack. If you're using a different road, if you're using a different satellite or a different terminal, those TTPs would come from Sparta from that perspective. But on using your ground against you, that's where the MITRE stuff comes in. And then you got to know, all right, at some point when you start interacting with like the front end processor, the crypto unit, or the TT&C software, then you need to look at Sparta TTPs on how they're actually going to do it, because MITRE doesn't cover that. So it's important to understand both.
Makes sense.
All right. Yeah, thank you again.